Hans Albrecht Bethe was a German and American nuclear physicist who, in addition to making important contributions to astrophysics, quantum electrodynamics and solid-state physics, won the 1967 Nobel Prize in Physics for his work on the theory of stellar nucleosynthesis. For most of his career, Bethe was a professor at Cornell University. During World War II, he was head of the theoretical division at the secret Los Alamos laboratory which developed the first atomic bombs. There he played a key role in calculating the critical mass of the weapons and developing the theory behind the implosion method used in both the Trinity test and the Fat Man weapon dropped on Nagasaki in August 1945. After the war, Bethe also played an important role in the development of the hydrogen bomb, though he had originally joined the project with the hope of proving it could not be made. Bethe later campaigned with Albert Einstein and the Emergency Committee of Atomic Scientists against nuclear testing and the nuclear arms race. He helped persuade the Kennedy and Nixon administrations to sign, respectively, the 1963 Partial Nuclear Test Ban Treaty and 1972 Anti-Ballistic Missile Treaty. His scientific research never ceased and he was publishing papers well into his 90s, making him one of the few scientists to have published at least one major paper in his field during every decade of his career, which, in Bethe's case, spanned nearly 70 years. Freeman Dyson, once one of his students, called him the supreme problem solver of the 20th century. Early years. Bethe was born in Strasbourg, which was then part of Germany, on July 2, 1906, the only child of Anna and Albrecht Bethe, a private docent of physiology at the University of Strasbourg. Although his mother, the daughter of a professor at the University of Strasbourg, was Jewish, he was raised a Protestant like his father. Despite having a religious background, he was not religious in later life, and described himself as an atheist. His father accepted a position as professor and director of the Institute of Physiology at the University of Kiel in 1912, and the family moved into the director's apartment at the institute. He was initially schooled privately by a professional teacher as a part of a group of 8 girls and boys. The family moved again in 1915 when his father became the head of the new Institute of Physiology at the University of Frankfurt am Main. Bethe attended the Goethe Gymnasium in Frankfurt, Germany. His education was interrupted in 1916, when he contracted tuberculosis, and he was sent to Bad Kreuznach to recuperate. By 1917, he had recovered sufficiently to attend the local Realschule, and the following year he was sent to the Odenwaldschule, a private, co-educational boarding school. He attended the Goethe Gymnasium again for his final 3 years of secondary schooling, from 1922 to 1924. Having passed his ๊hbʁɛçt, Bethe entered the University of Frankfurt in 1924. He decided to major in chemistry. The instruction in physics was poor, and while there were distinguished mathematicians in Frankfurt like Carl Ludwig Siegel and Otto Schaz, Bethe disliked their approaches, which presented mathematics without reference to the other sciences. Bethe found that he was a poor experimentalist who destroyed his lab coat by spilling sulfuric acid on it. But he found the advanced physics taught by the associate professor, Walter Gerlach, more interesting. Gerlach left in 1925, and was replaced by Karl Meissner, who advised Bethe that he should go to a university with a better school of theoretical physics, specifically the University of Munich, where he could study under Arnold Sommerfeld. Bethe entered the University of Munich in April 1926, where Sommerfeld took him on as a student on Meissner's recommendation. Sommerfeld taught an advanced course on differential equations in physics, which Bethe enjoyed. Because he was such a renowned scholar, Sommerfeld frequently received advance copies of scientific papers, which he put up for discussion at weekly evening seminars. When Bethe arrived, Sommerfeld had just received Erwin Schrödinger's papers on wave mechanics. For his PhD thesis, Sommerfeld suggested that Bethe examine electron diffraction in crystals. As a starting point, Sommerfeld suggested Paul A. Wald's 1914 paper on X-ray diffraction in crystals. Bethe later recalled that he became too ambitious, and, in pursuit of greater accuracy, his calculations became unnecessarily complicated. When he met Wolfgang Pauli for the first time, Pauli told him, "After Sommerfeld's tales about you, I had expected much better from you than your thesis, I guess." From Pauli, Bethe later recalled, "That was a compliment." Early work. After Bethe received his doctorate, Erwin Madelung offered him an assistantship in Frankfurt, and in September 1928 Bethe moved in with his father, who had recently divorced his mother. His father met Vera Congehl earlier that year, and married her in 1929. They had 2 children, Doris, born in 1933, and Klaus, born in 1934. Bethe did not find the work in Frankfurt very stimulating, and in 1929 he accepted an offer from Ewald at the Technische Hochschule in Stuttgart. While there, he wrote what he considered to be his greatest paper, Zur Theorie des Durchgangs schneller Korpuskularstrahlen durch Materie. Starting from Max Born's interpretation of the Schrödinger equation, Bethe produced a simplified formula for collision problems using a Fourier transform, which is known today as the Bethe formula. He submitted this paper for his habilitation in 1930. Sommerfeld recommended Bethe for a Rockefeller Foundation traveling scholarship in 1929. This provided $150 a month to study abroad. In 1930, Bethe chose to do postdoctoral work at the Cavendish Laboratory at the University of Cambridge in England, where he worked under the supervision of Ralph Fowler. At the request of Patrick Blackett, who was working with cloud chambers, Bethe created a relativistic version of the Bethe formula. Bethe was also known for his sense of humor, and with Guido Beck and Wolfgang Rieseler, 2 other postdoctoral research fellows, created a hoax paper on the quantum theory of the temperature of absolute zero, where he calculated the fine structure constant from the absolute zero temperature in Celsius units, causing a scandal in the scientific world. The paper poked fun at a certain class of papers in theoretical physics of the day, which were purely speculative and based on spurious numerical arguments such as Arthur Eddington's attempts to explain the value of the fine structure constant from fundamental quantities in an earlier paper. They were forced to issue an apology. For the second half of his scholarship, Bethe chose to go to Enrico Fermi's laboratory in Rome in February 1931. He was greatly impressed by Fermi and regretted that he had not gone to Rome first. Bethe developed the Bethe ansatz, a method for finding the exact solutions for the eigenvalues and eigenvectors of certain one-dimensional quantum many-body models. He was influenced by Fermi's simplicity and Sommerfeld's rigor in approaching problems, and these qualities influenced his own later research. The Rockefeller Foundation offered an extension of Bethe's fellowship, allowing him to return to Italy in 1932. In the meantime, Bethe worked for Sommerfeld in Munich as a private docent. Since Bethe was fluent in English, Sommerfeld had Bethe supervise all his English-speaking postdoctoral fellows, including Lloyd P. Smith from Cornell University. Bethe accepted a request from Carl Scheele to write an article for the Handbuch der Physik on the quantum mechanics of hydrogen and helium. Reviewing the article decades later, Robert Bethe and Victor Weisskopf noted that it was unusual in the depth and breadth of its treatment of the subject, yet required very little updating for the 1959 edition. Bethe was then asked by Sommerfeld to help him with the Handbuch article on electrons in metals. The article covered the basis of what is now called solid-state physics. Bethe took a very new field and provided a clear, coherent and complete coverage of it. His work on the Handbuch articles occupied most of his time in Rome, but he also co-wrote a paper with Fermi on another new field, quantum electrodynamics, describing the relativistic interactions of charged particles. In 1932, Bethe accepted an appointment as an assistant professor at the University of Tübingen, where Hans Geiger was the professor of experimental physics. One of the first laws passed by the new National Socialist government was the law for the restoration of the professional civil service. Due to his Jewish background, Bethe was dismissed from his job at the university, which was a government post. Geiger refused to help, but Sommerfeld immediately gave Bethe back his fellowship at Munich. Sommerfeld spent much of the summer term of 1933 finding places for Jewish students and colleagues. Bethe left Germany in 1933, moving to England after receiving an offer for a position as lecturer at the University of Manchester for a year through Sommerfeld's connection to William Lawrence Bragg. He moved in with his friend Rudolf Peels and Peels' wife Genia. Peels was a fellow German physicist who had also been barred from academic positions in Germany because his parents were Jewish. This meant that Bethe had someone to speak to in German, and did not have to eat English food. Their relationship was professional as well as personal. Peels aroused Bethe's interest in nuclear physics. After James Chadwick and Morris Goldhaber discovered the photodisintegration of deuterium, Chadwick challenged Bethe and Peels to come up with a theoretical explanation of this phenomenon. This they did on the 4-hour train ride from Cambridge back to Manchester. Bethe would investigate further in the years ahead. In 1933, the physics department at Cornell was looking for a new theoretical physicist, and Lloyd Smith strongly recommended Bethe. This was supported by Bragg, who was visiting Cornell at the time. In August 1934, Cornell offered Bethe a position as an acting assistant professor. Bethe had already accepted a fellowship for a year to work with Neville Mott at the University of Bristol for a semester, but Cornell agreed to let him start in the spring of 1935. Before leaving for the United States, he visited the Niels Bohr Institute in Copenhagen in September 1934, where he proposed to Hild Levi, who accepted. However, the match was opposed by Bethe's mother, who did not want him marrying a Jewish girl, and Bethe broke off their engagement a few days before their wedding date in December. United States. Bethe arrived in the United States in February 1935, and joined the faculty at Cornell University on a salary of $3,000. Bethe's appointment was part of a deliberate effort on the part of the new head of its physics department, Roswell Clifton Gibbs, to move into nuclear physics. Gibbs had hired Stanley Livingston, who had worked with Ernest Lawrence, to build a cyclotron at Cornell. To complete the team, Cornell needed an experimentalist, and, on the advice of Bethe and Livingston, recruited Robert Bacher. Bethe received requests to visit Columbia University from Isidore Isaac Rabi, Princeton University from Edward Condon, University of Rochester from Lee Dubridge, Purdue University from Karl Lark Horowitz, the University of Illinois at Urbana-Champaign from Francis Wheeler Loomis, and Harvard University from John Hasbrouck Van Vleck. Gibbs moved to prevent Bethe from being poached by having him appointed as a regular assistant professor in 1936, with an assurance that promotion to professor would soon follow. Together with Bacher and Livingston, Bethe published a series of 3 articles, which summarized most of what was known on the subject of nuclear physics until that time, an account that became informally known as Bethe's Bible, and remained the standard work on the subject for many years. In this account, he also continued where others left off, filling in gaps in the older literature. He wrote to his mother, "I am about the leading theoretician in America. That does not mean the best. Wiener is certainly better, and Oppenheimer and Teller probably just as good. But I do more and talk more, and that counts too." On March 17, 1938, Bethe attended the Carnegie Institute and George Washington University's 4th Annual Washington Conference of Theoretical Physics. There were only 34 invited attendees, but they included Gregory Bright, Subramanian Chandrasekhar, George Gamow, Donald Menzel, John von Neumann, Bengt Strömgren, Edward Teller and Merle Bethe initially declined the invitation to attend, because the conference's topic, stellar energy generation, did not interest him, but Teller persuaded him to come. At the conference, Strömgren detailed what was known about the temperature, density and chemical composition of the Sun, and challenged the physicists to come up with an explanation. Gamow and Carl Friedrich von Weizsäcker had proposed in a 1937 paper that the Sun's energy was the result of a proton-proton chain reaction, but this did not account for the observation of elements heavier than helium. By the end of the conference, Bethe, working in collaboration with Charles Critchfield, had come up with a series of subsequent nuclear reactions that explained how the Sun shines. That this did not explain the processes in heavier stars was not overlooked. At the time there were doubts about whether the proton-proton cycle described the processes in the Sun, but more recent measurements of the Sun's core temperature and luminosity show that it does. When he returned to Cornell, Bethe studied the relevant nuclear reactions and reaction cross-sections, leading to his discovery of the carbon-nitrogen-oxygen cycle. The two papers, one on the proton-proton cycle, co-authored with Critchfield, and the other on the carbon-oxygen-nitrogen cycle, were sent to the Physical Review for publication. After Kristallnacht, Bethe's mother had become afraid to remain in Germany. Taking advantage of her Strasbourg origin, she was able to emigrate to the United States in June 1939 on the French quota, rather than the German one, which was full. Bethe's graduate student Robert Marshak noted that the New York Academy of Sciences was offering a $500 prize for the best unpublished paper on the topic of solar and stellar energy. So Bethe, in need of $250 to release his mother's furniture, withdrew the CNO cycle paper and sent it into the New York Academy of Sciences. It won the prize, and Bethe gave Marshak $50 finder's fee and used $250 to release his mother's furniture. The paper was subsequently published in the Physical Review in March. It was a breakthrough in the understanding of the stars, and would win Bethe the Nobel Prize in Physics in 1967. In 2002, at age 96, Bethe sent a handwritten note to John N. Barkhall congratulating him on the use of solar neutrino observations to show that the CNO cycle accounts for about 7% of the Sun's energy. The neutrino observations had started with Raymond Davis, whose experiment was based on Barkhall's calculations and encouragement, and led to Davis's receiving a share of the 2002 Nobel Prize. Bethe married Rose Ewald, the daughter of Paul Ewald, on September 13, 1939, in a simple civil ceremony. They had two children, Henry and Monica. He became a naturalized citizen of the United States in March 1941. Writing to Sommerfeld in 1947, Bethe confided that, "I am much more at home in America than I ever was in Germany, as if I was born in Germany only by mistake, and only came to my true homeland at 28, Manhattan Project." When the Second World War began, Bethe wanted to contribute to the war effort, but was unable to work on classified projects until he became a citizen. Following the advice of the Caltech aerodynamicist Theodore von Karman, Bethe collaborated with his friend Teller on a theory of shock waves which are generated by the passage of a projectile through a gas. Bethe considered it one of their most influential papers. He also worked on a theory of armor penetration, which was immediately classified by the Army, making it inaccessible to Bethe, who was not an American citizen at the time. After receiving security clearance in December 1941, Bethe joined the MIT Radiation Laboratory, where he invented the Bethe hole directional coupler, which is used in microwave waveguides such as those used in radar sets. in Chicago in June 1942, and then at the University of California, Berkeley, in July. He participated in a series of meetings at the invitation of Robert Oppenheimer, which discussed the first designs for the atomic bomb. They went over the preliminary calculations by Robert Serber, Stan Frankel, and others, and discussed the possibilities of using uranium-235 and plutonium. Teller then raised the prospect of a thermonuclear device, Teller's super bomb. At one point Teller asked if the nitrogen in the atmosphere could be set alight. It fell to Bethe and Emil Konopinski to perform the calculations to prove that this could not occur. The fission bomb had to be done, he later recalled, because the Germans were presumably doing it when Oppenheimer was put in charge of forming a secret weapons design laboratory, Los Alamos. He appointed Bethe director of the T Division, the laboratory's smallest but most prestigious division. This move irked the equally qualified but more difficult to manage Teller and Felix Bloch, who had coveted the job. A series of disagreements between Bethe and Teller between February and June 1944 over the relative priority of super research led to Teller's group being removed from T Division and placed directly under Oppenheimer. In September it became part of Fermi's new F division. Bethe's work at Los Alamos included calculating the critical mass and efficiency of uranium-235 and the multiplication of nuclear fission in an exploding atomic bomb. Along with Richard Feynman, he developed a formula for calculating the bomb's explosive yield. After August 1944, when the laboratory was reorganized and reoriented to solve the problem of the implosion of the plutonium bomb, Bethe spent much of his time studying the hydrodynamic aspects of implosion, a job which he continued into 1944. In 1945, he worked on the neutron initiator, and later on radiation propagation from an exploding atomic bomb. The Trinity nuclear test validated the accuracy of T Division's results. When it was detonated in the New Mexico desert on July 16, 1945, Bethe's immediate concern was for its efficient operation, and not its moral implications. He is reported to have commented,